medical things, and so, and like what steps you would take. So I talked about how like you would take your shoes, examine them, but I didn't say like swab the blood, I just said examine for trace evidence. Circle trace evidence, drew a line to blood, and very aggressively circled blood.
I think most students don't that blood. I was trying to get you guys again, because you're going to go into your field and you're going to become specialized, right? When you go to the crime lab, and the problem is that you become blinders. If that's the only thing that you know, that's the only thing you're going to see in that piece of evidence. And I'm trying to make sure that you recognize that there's a heck of a lot of other things that you need generalists, criminalists to get the most out of the piece of physical evidence. Because like I was saying, like gun guys, a lot of times get bullets with blood or something in them. And a lot of times just pick the stuff off. That can be super valuable for reconstruction. Okay? Or there's a photograph and there might be a fingerprint, but I'm a footwear guy. You know, just really receptive of other things that are not just your own thing. That's what I'm going to do. I'm just promoting DNA there, man. See?
Yeah, it's
Not
really rare.
DNA.
Good for you.
Or the doghouse club.
So question, what are the weighted, what's the weighted and everything?
A lot.
The way of everything. It's on the, you have that, it's in the syllabus.
Yeah, I just didn't want to pull it up.
So it's like, yeah. So each lab's with 100 points, midterms on 500.
It's 4%, I think. Each lab is 4%.
Did you say each lab is 4%?
Yeah.
Yep, there you
Yeah,
go.
4%.
Okay, so it was
Yep, so, yep.
you have to scroll up on the page, not on the window that the PDF is
There we go.
But we only have 9 labs now.
Yes, right, so things are going to be shifted a little bit.
at. We're going to take that 4%, move across the Or whatever lab we all did amazing on, just make that
Drop
one
it, because it's not worth it?
No!
Make that double.
That was footwear, everybody got footwear.
No.
Right? Well, you know.
And he wouldn't tell me what I
Oh,
was
yeah,
saying.
everybody got footwear. That was good, that was.
It's not know. I got my ladder.
Interesting. Maybe because she just.
Hair was a different story, but.
Oh.
What was that? Hair was hard. Hair is hard. Yeah, yeah.
It knows a lot to it.
Can you go over 20 on the midterm? The cubic crystal and the differences at different wavelengths?
Oh, yeah. You're gonna kick yourself because how it's really.
I'm sure it's like stupidly easy, but I
Mm.
just.
No, it's fine. Yeah. Okay. So,
I want to help straight away.
what is? So, I guess number one, what is the indicatrix of an isotropic material?
Circular.
Sphere.
Sphere, sorry.
Yeah.
Yeah.
Yep. And that's because wherever, regardless of what direction light is vibrating, it's essentially the same electronic environment regardless, okay? That's why in tetragonal and hexagonal, those are uniaxial because they have different, when his light vibrates differently, or vibrates in different directions, it experiences different refractive indexes. So they have uniaxial indicatrix, and then orthorhombic, monoclinic, triclinic have biaxial. Okay? So those are the three optic classes, which I think was one of the questions as well. So the draw the matrices for a cubic crystal, the significant dispersion, so it's, what's dispersion? Difference in refractive index and wavelength. So it's saying it's very, very big. So the RI is much greater for 450 than 650. Okay. So I'm just going to draw the first one. That's it. It's a circle. Or it's a sphere. So I'm saying the 650. So now, what would I draw for 650? So here's a question. This is again going back to the same thing. What is this? What is the indicatrix?
Mm-hmm.
With vibration direction, sure. Yep. And so every radii out of here is essentially the exact same, right? That means that the radii is, or radius is proportional to the wavelength, or is proportional to the refractive index. So I'm saying that the RI is much greater for 450 than it is for 650. Greater, which is right. Shorter wavelengths typically have higher refractive index. So, what would I draw here?
Smaller.
This question. That's all I, do you understand why? Why, because I said, so you have to understand what, okay, so there's a couple things you need to understand to answer this question. First, you need to know an isotropic material has a spherical indicatrix. And the next thing you need to know is that the length of it, the radii, are proportional to the refractive index. I told you this one is lower refractive index than this one, so that just tells me, okay, I just need to make a sphere with shorter radii.
So all cubic crystals are isotropic.
Yes. And yeah, glasses are also, yeah, anything that does not have a crystallinity to them, long-term crystallinity is called isotropic material, like a glass. Liquids, gases, and any crystal material that's in the cubic system, like table salt, would be an isotropic material. So are we clear on what was going on here? Yeah.
Why the lower wavelength has a greater eye?
Dispersion is almost always shorter wavelengths for a given material. It's almost always the case that the shorter wavelength is going to have a higher refractive index than the longer wavelength. The wavelength, so the way I think about it is the wavelength is much tighter and smaller, so it has more opportunity to interact with the electron cloud than a longer wavelength. That's probably BS, but I conceptually understand it that way. So, you good? Yeah. Next. Wherever we're good at. All right, how about we just do the midterm and page 4, interference figures. I don't know if these are problematic. Yep. Okay, so it says, at 45 degrees off extinction, draw the acute bisectrix for a for a negative optic sign crystal. Okay, so if I have a interference figure, we typically look at them in one. There's typically one of two positions we're looking at. That looks kind of like a biaxial or uniaxial crystal. But if I were to rotate this stage now, the isogyres would open up to like that. That tells me I've got a biaxial. This is at extinction at 0. And when I have them opened up where there's the maximum separation of those, that's at 45 degrees off extinction. Okay? So it's asking to, at 45 degrees off extinction, so essentially saying draw this. Now, we could have drawn it this way, or we could have drawn it this way. Doesn't matter. We just gotta know what's what. Location is key there. I typically do that. Okay, so it says the acute bisectrix. Okay, so remember we've got, I have a biaxial crystal here. And so here is alpha, here is gamma, and let's say I'm gonna draw. So those are the two betas, right? But then what's 90 degrees to them is optic axis 1, optic axis 2. You all good on that? Yep. Okay, so now, so we can have, this is one of two flavors here. We can have it where the optic axes, so there's this angle, or there's this angle. Those are complementary, right? So we got this bit plus this bit will add up to 180 degrees. You all good on that? Yeah. So one of them is the acute, one is the obtuse angle between those two. Did I draw that right? No, I did. Yeah.
Yep.
Yep. We got optic axis 1, optic axis 2. So we got this angle. So this would be the obtuse, and this would be the acute angle here. And so, so this again, going back to just, this is somewhat of a memorization. If the acute angle here is bisected by gamma, we have a positive optic sign. If I were to redraw this now, and now I'm just going to draw the optic axes here, not beta. This is the acute, and then this would be the obtuse. So this would be a negative optic sign. Okay, so again, that's memorization. If the optic axes, if the acute angle between them is bisected by alpha, it's a negative. If the acute is bisected by gamma, it's positive. That, unfortunately, that is memorization. Okay. So, the question says, I have a negative optic sign. So that means I'm drawing, that's a terrible arrow, I'm drawing this guy. Not this one. So, that means I'm gonna be looking right here, in this direction. So if I go to here, this is one thing you can do regardless. If you don't know anything about what's going on, one thing that you can do, draw these, draw your line here. Here's the optic axial plane. Right here is one more optic axis. Here's the point of another optic axis. And what's perpendicular here? Beta. Okay? So, here's an optic axis. Here's an optic axis. So what is bisecting that acute angle right here? Which one? Alpha. Yep. Alpha's coming right out. So that then means it just has to be, then this way is gamma. And that's it. That essentially is the answer to that first question. Are we clear on that, sort of ish, maybe, kind of? Yes, no? You're good. You guys good? Yeah. What's the missing, where are you getting the stoppage? These are just straight memorization. I mean, these are just draw them over and over again, straight up memorizing.
Yeah, that's the problem.
Yeah.
You don't have those memorized, so that when you moved over to the picture on the far left, and you drew beta, and you just knew that alpha was coming out, I was like, I don't know how to do that.
Well, okay, so I said this was an optic axis emerging, this is an optic axis emerging, and this is the acute. Right there. What am I looking straight at me? What's looking, if I'm here, looking this way, what's coming out right at my face? Alpha.
Oh, so because we already
That's
knew
right
that
there.
it was a negative,
Yep.
and knew how to draw that properly.
Everything else just flows right out.
Okay.
Yeah. This is literally just a restatement of this. We didn't derive anything from it. It's the exact same thing. So you could, well, yeah, you could memorize this associated with that, but that's a lot of memorization. I just remember, here's what you're looking at. Because we're going to pull a bit of a shenanigans on the next question. In that we now have a positive sign. You guys are good, did you get that?
Yeah. I really don't mind, I'm writing on it. But it's already marked up with red.
Yeah, you have to get that.
I know.
Yeah, okay, so. All right, so now it says here, 45 degrees off extinction. So we kind of already know that we want to have these opened up. At 0 is kind of boring, so. Now we need to know the obtuse bisectrix for a positive optic sign. So, which model am I looking at?
Left.
Left, okay. And so, okay.
Wait, it's still.
Where would I draw? So I said it's an obtuse bisectrix. So where do I draw the isogyres? This is the obtuse now. Remember the acute was quite small. So what would you think that would happen if, so, okay, let's just draw those. There's a very small
10 degrees, probably.
That's really bad.
15.
Okay? That's maybe 10 degrees, that's a very, very acute. There's maybe, I don't know,
16,
60, 70,
70, 80,
80,
90. There's no isogyre.
something like that. So that's outside of this field of view, actually. Now, did you know that purpose? I mean, I don't know if you would know that, but just, I mean, if you would do something really, really big, I'd be okay, but technically, these things are outside of the field of view. When they open up, they're opening up so big that they actually leave the field of view. You actually can't see them. But when you start closing you're rotating the stage, they'll come into center again. Yep. Okay. So now we know we've got an obtuse. We can still draw this guy, OAP, and we can still know we've got this. Now, what's that? Sorry. So I said we are looking at the obtuse bisectrix of positive. So which am I looking at?
The dotted line, that one.
The dotted line, right? Yep. Because that's the key, or that's the obtuse angle here. Remember, here's the obtuse, or the use my words. Obtuse angle, acute angle between optic axis 1 and 2. So, what am I looking at? What am I looking at? Where am I looking this way?
No.
Or am I looking this way? Looking at alpha.
So.
Yep. So that means
That's common.
it's essentially the same exact drawing.
Without
The first one,
isotonic.
just with these moved out. That was the shenanigans.
Can you show how the lines would look like? The
Isochrones?
isochrones, yes.
Yeah, so they're going around here as well. But they're gonna go something like this. I mean, you might see some going across the field of view, but you won't see very much. You might just see some lines here. Are you following that one? Sort of? So, I mean, these drawings here are really key in recognizing the difference between the acute and the obtuse. That essentially, if you understand that, you equip yourself for pretty much any question I would ask you in relationship to that. Anything else?
Info over number 9.
Yeah. Okay. So it says calculate gamma minus alpha, gamma minus beta, or beta minus alpha if there's sufficient data from the following biaxial crystal. It's in the same set. Okay, so we're back to our 0.03 millimeter, which should be 3,000 micrometers, which would be 30,000. Okay. A positive crystal displaying a precisely centered acute bisectrix, third order yellow crosshair. Okay. So what do I draw here? What's my interference figure? What should I draw?
It's alpha.
Alpha's where? Coming out or this
Oh,
way?
no, that way.
No, it's gamma is coming straight out at us. Right? You got that? So, if gamma is coming straight out at us, what two refractive index values are, so I've got a fast ray and a slow ray. I've got a fast ray going in this direction. I've got a slow ray going in this direction. So, beta minus alpha is birefringence. And then what again? So this equals to thickness times birefringence. Okay. So my retardation value is 1500 nanometers. My thickness is 30,000 nanometers times birth. That's a great one. That equals to 0.05. So that means beta minus alpha is equal to that. What's that?
I said that's all you were looking for?
That's it.
Where are you getting the 1500 from?
I give it to you in the question.
Ah,
As that is the third order. That's the interference colors that you're seeing right here. Okay. So that's that one. So we gotta remember that. This is I think I gave extra credit for this answer. Tried to create some. That was beta minus alpha is equal to 0.05. Okay.
So was question 9 20 points, so it was 10 for A and 10 for B?
Correct. Yeah. Although I think, yeah, that's right. I think I have to regrade it, in that, well, the question about could A and B possibly represent different orientation of the same crystal? That's very hard. So that was actually, I turned that into an actual credit question.
Right.
That specific question. Okay, so now we have a positive crystal with a centered obtuse. So now we're going to go like this. Draw OAP, and we've got this guy here. Showing first order, so the is equal to 550. Okay. So, question is, we know beta here, so what's here and what's coming straight out at us?
so alpha is the,
So let's go back. So we know we have a positive crystal. Okay, so I'm just going to draw this guy. I'm not going to draw beta. I'm just going to draw the optic axes. I just find it easier. There's alpha, there's gamma, OA1, OA2. And I said that we're looking at the obtuse. So that's here. So we're looking, alpha's coming straight out at us, so that means gamma is going in this direction. Do you follow that? Yeah. Okay, so our birefringence that we're observing is gamma minus beta here. Because those are the two refractive index values that we can see here. Okay, so now all I'm going to redo is the equation, right? So 550 is equal to 30,000 nanometers times B. B is equal to 0.018. That is it. Do you follow that? Now, question is, so here is what, alpha, gamma minus beta must be greater than beta minus alpha for a positive crystal. So beta, this one here is 0.018, and this one over here is 0.05. This violates that, right? This is actually not bigger than this, right? Thus, those cannot be the same crystal.
If you gave that, I wouldn't come right.
What's that?
I say if you gave that, not the equation, yeah, but
This?
that, yeah.
That's the true method. I don't teach it typically like this,
Oh,
but if you, because again, I hate memorizing stuff.
yeah.
And so this is actually, if you look up in the textbook, this is how they define a positive crystal. And you're like, to me, that's just a scrolling a bunch of blah, 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 this minus that, and it's switching stuff. So I find this actually more confusing. But if you think about it though. So let's draw this. You can derive it actually. So this is beta here, right? So gamma minus beta in this crystal is bigger
Oh,
than beta minus alpha, right?
that makes sense.
This distance from here to here is bigger or is less than this distance to here. So that's how they truly teach that in the textbooks. But again, I find it, it breaks my head. So I don't typically like it. That's why that's probably a bit too harsh. So that's why I need an extra credit.
Mm.
We all good in that chart? Yep. Are we all good on XRF stuff? Yay, nay? Yeah, hopefully you'll see, like, when you're interpreting, like, no, Daniel yesterday was, and he was well, looking at all the peaks that were in the X-ray spectrum, and he was well, right? Looking at the,
Mhm.
you can really see a lot of, like, some peaks and escape peaks and all that stuff. And that was really kind of cool to see all that. That was really the empirical side of this theoretical stuff. So that's pretty neat to see all that. I thought.
I'm confused about your grading.
Not my grading, sure.
So like, you said, like, if it's just a line, you meant to put a check mark?
Oh.
Or is it supposed to be, because like,
Good being all good.
then why is there minus 20 points? Like, that's what I'm confused
Oh, wait,
about,
okay,
because if it's
yeah.
all check marks, then where did the negative come from?
Because this one's totally wrong. This last one is wrong.
Okay, so that last one should have been X.
X, yeah. Actually, that's they even have minus 20 next to it.
Yeah, well, that's what I figured was that last
Yeah,
one
yeah,
was
that's-
wrong,
that's
but you
the-
said
yeah,
that
that's-
like the
that's-
lines.
Yeah, let's go with that one. Yeah, so that question here, let's just make sure, there's, again, those are some important parameters there to understand. Yeah, yeah. Okay, so the question is, I need to detect uranium, okay? All the other stuff aside. So I've got my source is rhodium. And I'm operating it at an accelerating voltage of 60 kV. Okay, so if, listen, do you have that QR table? Can I grab that from you? So if I were to say, draw me what the spectrum of the source would look like. If I were to just have no sample in place, I would just look at what the source looks like. What would I draw?
Sure. Like a curve.
Okay. That,
If it-
Wouldn't it be spiking at RH?
Yes.
hold on, yeah, you're, well,
You'd have RH peaks.
you guys, here's one for you. And here's one for you. What did you see?
But it's not static, it's going with the source or range of energies.
But so when you're looking at the XRF data, it will tell you, like it shows you the source's peaks. So the source, like you can see them. So like, it's not like IR where there is a background that gets subtracted out. You essentially just ignore those peaks or the system flags them as RH, so you know that they're not part of your sample.
Was there not a chart with the different source backgrounds?
Mhm.
They don't look like that.
They don't, yeah, she's right.
Okay.
Yes, so yes, that's an important thing to realize, is that, so we have a background like this, it's kind of like that. And then we do have superimposed, so this is like K alpha, this is K beta, L alpha, L beta, and we can actually go to that chart and put precise values for that. So we go to those. So that'd be, so this one would be 20.21, this one would be 2.27, this would be, oops, 2.6, 2.70, and this is 2.83. Exactly. That's what I should see if I were to look at it. Now, what the hell is all this? That's the background. Why do I get that? Is because I've got a chunk of metal, rhodium metal, and over here, I've got a filament that is giving off electrons, and it's just accelerating at 60 kV, accelerating voltage at my source. Those electrons are beating the heck out of it so much that it starts irradiating X-rays all over the place. And if I were to collect all those X-rays, this is my spectrum of the source. So you actually, if you had no sample in there and you cranked up the gain on those spectra that we look at, you'd see a hump like this. They're just so overblown by the big peaks coming from the transition peaks. Okay. Okay. So,
Is that what happened with some of our tapes?
mm,
Because the front, like,
oh yeah, some of them are really
at
noisy,
the, at the
right?
spectrum,
I don't know what that is.
there's a whole hump at the beginning.
I know, I don't know what, that's really intriguing. I found that too. I don't know what that is. I don't know. I need to do some further investigation as to why those particular ones are doing that. I have no idea. Yeah. Okay, so I have X-rays that are ranging anywhere from 0 all the way out to my accelerating voltage of 60 kV. So the question is, with these conditions, can I detect uranium? So if I go look at my periodical table, alpha is equal to 98.43. K beta is 111.29.
Okay.
Can I accelerate or excite those? No. I don't have enough sufficient energy. If I go, here's my very simplified uranium particle. I don't have enough energy. I need an incoming X-ray to knock this particle or this electron off for an electron from the L to come in here. And that energy is 98. The best I can do is 60. So I am grossly under the accelerating voltage needed to excite that K alpha. I don't know if it's the same in X-ray fluorescence, but in scanning electron microscopy, SEM-EDS, you like to be 2 times that. So in reality, you like to be at 200 to get this efficient. I don't know if that's the same thing in X-ray fluorescence, but I'm assuming it's probably close to that. So you do like to have things higher than the minimum, it's just for efficiency point of view, okay? So that means that no, I can't do this one. I certainly can't do this one. But now, okay, I can't do the K lines, but what about the L lines? L alpha is 13.61, L beta is 17.22. Let's see right there. I have plenty of overvoltage to excite those, so the answer is yes. Under these conditions, I can get these lines coming off the uranium. So there's a lot, to answer this question again, is pulling in, you're looking at it like, oh, that's pretty simple, but it's pulling in a lot of concepts in a simple question here. Understanding this, understanding the background here, and then also understanding what do I need to actually generate a particular X-ray, and then also understanding there are multiple lines, and I might be able to go after different lines. Okay? So in SEM, scanning electron microscopy, a lot of times you want to detect uranium in a particular element or a particular mineral. There's no way that we're going to get anywhere near this in a scanning electron microscope. The accelerated voltage is 25 to 30 if you're really beating the heck out of your instrument. So you have to go for these L lines. Or you can even go for the M one, which are even really low energy. So you kind of have to adjust what you're looking for depending on what your system can do. Okay. Any issue?
I didn't get the entire question wrong on that. Because I said that you could detect uranium, it would just be difficult.
What was that?
Well, okay, but like partial credit, come on, like I knew, because I know that the instruments that we have, it can detect uranium, but she said that like it depends on a lot of factors, and like she rambled off a lot of factors when she was going over the training and stuff.
Yeah.
And so like I couldn't remember specifically, but I did know that like, I granted it wasn't specifically what you covered, but I said that it could detect it, which is true. That was one part of the question. I just incorrectly said how. Well, I mean, it's a 20-point question, and I got all 20 points wrong, even though I did get it right that you can't detect it.
But the foundation was not there to get to that. It's a 50-50 guess.
Well, okay, but based on the rest of my explanation, I wasn't just guessing. I did talk about like some parameters that would affect it. They just weren't specific to uranium. They're just for any simple thing.
I can do a little bit again. Make sure you know ace B.
Not that one. Not ACE again.
just briefly, the, like, persistence and permanence, you talk about like the footwear? I feel like I don't fully understand it.
Yeah, like some of these people used to say that, you know, you have the individualizing mark. You'd love to have it as permanent, right? That mark is always there for, you know, the life of the shoe. But you don't necessarily need to have that. It just need to be, it needs to be present to make the mark, and then to also be present when you are making like a comparison, like you're making exemplar prints from it. You still have those individualizing characteristics are on the question that the scene, and also the one that you're making. Okay?
Okay, so like a
Because things
default,
can constantly change.
like a defect in the sole, like an air bubble, would show up, but if the shoe is like heavily worn,
It'll be gone.
it's gone,
Yeah.
so it's
And
not
then-
permanent, it's just persisting because it
Yeah.
show up enough times until it wears out.
Yes. Yeah,
Okay.
yeah.
So I did get that. I was like, I'm going through the notes and I highlighted that because I wasn't sure if I did persistency and permanence well.
Midterm number 8. I got the first part, right?
Which one, number 8?
Yeah.
Oh, I want to measure the maximum and minimum refractive index values for uniaxial crystal. So what are the maximum and minimum? For uniaxial crystal.
Omega and
Omega.
wait, omega and epsilon.
And epsilon. Yep. Those are the two end members. This could be higher than this, or this could be higher than this. We don't know that answer. That would tell us if we have a positive or negative crystal. But those are the two end members. And everything in between here is an epsilon prime. Okay. So, how do I measure both of those? This one is fairly easy. This one is fairly easy. This one's a pain in the arse. Because it needs a very specific orientation. And if I have, so here's a uniaxial, you know, this happens to be a positive one. Doesn't matter. Okay. So if I have some crystal, if I have a calcite, let's say, that's the actual, well, it says quartz, because it's positive. We bust up into a bunch of pieces. Remember, the orientation of the indicatrix doesn't change inside the crystal, but when you break it up, right, then that orientation, and the particles can be all over the place, but they're still ultimately going to have that same orientation inside, right? So if I had a quartz crystal and I busted it all up, I once had a nice, perfectly formed crystal that looked like this. I'm very happy. Everything is oriented this way. I know everything about it. Now, if I bust it up, I've got these particles that are all over the place, right? And that epsilon value could be all over the place, or epsilon, the full epsilon, right? Or this is also coincides with the optic axis. So let's just say the optic axis is all over the place here. In almost all these crystals, I will be able to measure an epsilon prime, and if I rotate the stage, so at one extinction position, let's say I measure its epsilon prime, 90 degrees to that, I'll get omega. Pretty much always. Depending, I mean, almost always, like a random sprinkling, you're gonna get an epsilon prime and an omega. Omega is gonna be consistent with the okay? But you'll have some varying epsilon prime. But how do we get this guy? So how would I want to get, so if light comes up here, it's only going to, remember I always project it to the center, right? So it's vibrating here, that's going to be omega. If it's at some other angle, it would be omega and then epsilon prime, okay? So how do I get light to vibrate in this direction?
You lay down like 90 degrees.
That's the answer. I've got,
Okay.
Yep.
Okay.
I've got my crystal sitting, like here's the plane of the microscope. If I'm here, the optic axis is straight up and down, all I'm gonna see is omega. If I rotate it perfectly flat, one orientation is gonna be omega. I rotate it 80 degrees, and we're gonna get the full epsilon value. So if I can get that c-axis to lie perfectly flat on the stage of the microscope, I can get the full epsilon value. You ever got that? It's hard to do. To get it perfectly lined like that, but there's ways you can actually do that. But what you want to do, okay, so here's a quick question. If I've got, if the c-axis is sitting just like this on the stage of the microscope, I look down on it, I cross the poles, what am I going to see? C-axis comes straight at me. What's another name for the optic axis or the c-axis? Axis of isotropy. It'd be extinct.
Distinct.
Because all I'm doing is light is coming up here and it's experiencing only omega, so it's only experiencing one refractive index, so it's painted on
nothing.
glass or cubic crystal. Now, what about this guy? So, okay, okay, so now I'm at an angle here like this. Now I'm just generally, not asking specific, what the heck am I going to see when I cross the poles? Just generally. Is it going to be black?
No.
No. You'll see some type of interference colors, right? Okay, so yeah, you'll see some, depending upon the birefringence and thickness, you'll see different interference colors. Okay, now, how am I gonna do this? That's getting a little more confusing. So as I rotate, I had only omega. Now I'm getting an epsilon prime value. And as I continue to rotate it, I'm getting higher and higher values of epsilon prime. So as I'm going like this, what's happening to my birefringence value? As I'm dropping this guy down lower and lower.
Greater.
Yep, because I'm getting higher epsilon prime values, so the difference between epsilon prime and omega is constantly going up and up and up and up and up. Until, what about now? Now what's it going to be like?
Epsilon.
Exactly right. Because I'm getting omega, I'm getting light that's traveling to omega, and I'm getting light
Epsilon.
that's traveling in the full value of epsilon. So those are the two absolute n-member wave or refractive index that I can get. So that's going to give me my biggest birefringence that I could experience with this crystal. In that, so if I have a sprinkling of a whole bunch of crystals here and I'm trying to find something that may be kind of like this, I'm going to try to find the brightest particle possible. Because that is going to be my best chance of being pretty dang close to having the crystal sit like that. Provided that everything is roughly the same thickness, right? Okay. If I wanted to find omega, if I'm trying to find a really beautiful interference figure, and a nice centered one, I'm going to look for either one that's all black or really the lowest possible interference colors, because there it's going to either be just omega or maybe omega just a little bit of epsilon prime. It's going to be so damn close that it'll be like this, maybe just a little bit angled. Are you clear on that? That's a good concept.
So when it looked like this, could you also say birefringence 0?
0.
So there's no retardation.
Yeah, correct.
Okay, that's why it's pitch black.
Yeah.
Okay.
What else we got?
Oh,
What's that?
I said, okay. Just clarification question. Okay, directionality of the tool mark is making sure that like your mark and your like sample, like your K and your Q, are both running the same direction.
Yeah.
But then the path is like, okay.
Yeah, sure. Yeah, because one is like dragging, and the other one is plowing. You know what I mean?
Yep.
So that could potentially need different marks.
Okay. A little confused when reviewing the PowerPoints about the drilling of firearm barrels. Is the range broach, the
Gang broach.
game broach,
Yep.
is that the second to last thing?
So you have the metal, you have the stock, right?
Yep.
Pete cover all this stuff? It's pretty good.
He did, but the two of you don't like to put a lot of words on your slides, which I
He's worse,
understand.
yeah, he's worse than I am.
But it's like when I'm then trying to go
Yeah.
and put the steps in order, and it literally just says the names of all of them, I'm like, okay, that's not helpful.
Yeah. So, right, so you have your stock, you know, your metal stock, but it doesn't have a hole. Then it has its deep hole drill, so it's digging out the first hole right down the center of it. So
And
now
it's
it's
like
like,
the time.
yeah, now it's turning it a bar into a tube, okay? And so that's pretty rough cut, but it has not done anything to impart rifling characteristics on it. So the gang broach is one way to cut the rifling into the barrel. You can also do a button broach as well. That's where that thing is, it really gets shoved right down and just forces the metal out of the way.
Okay.
So there's that, so you can have it, you deep hole drill, I guess you ream, and then you rifle it.
So, no, so the slides have it as first you do your centering type hole.
Yep.
Then you do, you could do
Right.
like a larger hole, or you just do the gang broach, then you ream at the end.
Oh,
to
yeah.
complete that.
I get those constantly, I don't know if, I get those two mixed up all the time.
Okay, so it's supposed to be like
Whatever the
a tiny
slides.
hole.
Yep.
Well, and then like they don't say anything, they're just, that's the order of the pictures that you put. 'Cause
Okay,
you
yeah.
put the pictures of the tools, you didn't
Yeah.
put any explanation.
Yep,
Okay, so that's the order, so that's cool.
Yep.
Good. Another slide that was just a picture. The IBS system, you
Mhm.
want us to describe it, you literally just have a picture of a computer.
Yeah, we talked about it. It's
I
just
don't
an
remember.
integrated ballistic identification system. So that essentially, I wish Winters was gonna give you guys a thing on it. So that is a automated database system that crime labs, I think all crime labs have access to. They actually have dedicated technicians that work with this stuff, where they will photograph cartridge cases and bullets in incredibly controlled conditions. It's really super highly controlled how the things are photographed. And so those, so if a gun is used in a crime, they'll take exemplars of bullets and cartridge cases from that gun and take these really highly controlled photographs and put them into a database that you can query. So it allows you to say, if you've got a shooting that you don't have a gun, you can query the database to see if this gun was used in another case.
So it's like CODIS but for firearms?
Yes, yeah.
Okay.
Yep. Okay, yeah.
I knew it was like a database, but I couldn't remember like the exact thing about it, but it was just.
Yeah, so they essentially searched to see if this gun was used in we had a case where this guy's gun was used in another homicide. Just getting toast.
So when you're talking about like the three different lines for the X-ray, you're talking about like K alpha.
Oh, yeah,
didn't get all the way through the X-ray lecture before this class today, that's what I was going through earlier. So this might be on the actual lecture, but the one thing I highlighted was the
Bremsstrahlung.
that characteristic of the X-ray.
Yep.
Don't remember what that is.
You do now.
So, okay, so it's the
hump.
hump.
Yep.
The hump.
Yep, it's the background. Yep. It's called Bremsstrahlung is braking radiation. German.
Was drawn on the board when Alex was right.
Memorialized.
Oh, so, okay, you say you hate memorizing things, but then you told us to.
Sometimes you have to.
But it says like what are additives, pigments, extenders, and fillers. We don't have to know the specific ones. We just have to know like what they are.
Yeah, what they're. I mean, having an example would probably not be a bad idea.
But we don't like your slide that said like additives. It could be this kind, which is a polypropyl blah 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 blah.
Yeah, okay. Like, what's a filler? Give me an example of filler.
Okay.
Just rather should do what?
Talc.
Talc. Good. Perfect.
Okay.
Calcite. Good. Or yeah, calcite.
Shoot.
TiO2. Iron oxide.
See, that's what I was gonna say. I'm also worried. 'Cause,
Ferrite. And I mean, those fillers are used in paints and polymers and they're used over and over and over again.
A lot of the stuff I had highlighted was some of the like calculate and find and marry.
So,